Next step, we want to find the solution. We want to, so here, find the solution. Here the question is, because we can write a program to implement this recurrence relation with a function. That is very easy, right? Yeah. So here the question, to write a program to implement this recurrence relation is easy. Okay. Yeah. We do not need to, write a pseudocode here, because everyone can do it easily. But here, let me give you some general problem-solving fact. Okay, problem-solving fact. Yeah. So that is, if you can find a formula it is the best solution. Okay, yeah. So here, although we can do it in this way, all right, just write a program that given n, it will return the answer. So that is a solution. We have it. But another thing, because we want to find a better solution, right? We want to find a better solution. Here, I like to convey this point. That is, if we can find a formula for the solution, math formula for the solution, we just plug in a number, we do the calculation, we do not write a program, right? Because we have a formula, all right? Or we just write a program to evaluate the value using this formula. That will be much faster than your, program implementation from the recurrence relation directly, because you need to do a lot of recursion, right? In my formula, if I have a formula when I plug in, I do not need to do recursion, right? I just do calculation, simple calculation. Yeah. So that is the, reason I say, if you can find a formula, it is the best solution. It is much better, much faster than your, recursive implementation. Here we want to do that. Here we want to find a math formula. All right, yep, okay, all right, so here. That means we want to solve this recurrence relation. Okay, we want to solve it. Yeah. All right. So when we solve it, so let us continue our analysis here. Look at this integer division, n over 2. That is a special division because the denominator is 2. So we can treat it as a shift operation, left shift operation. We move the decimal point, but here let's say the binary point, right? Okay. So we have some bits. Then point Okay, yeah, because the integer, the point, and the fractional, okay, the structure. But integer, we drop the fractional part. Then division by 2, we just move this binary point one position to the left. And well, after we move, we drop the bit after the binary point. Okay, yeah. And the good thing is, this operation is very fast. You just move position, left shift, much faster than addition. Addition, you need to do a lot of operation, a lot of internal basic operations. And the moving binary point, left shift or right shift, extremely fast. Okay, so that kind of special integer division, very fast. Okay, yeah. All right. So then, yeah, it is faster than addition. Okay, all right. So then, for this question, the basic operation is addition. Yeah, every time we need to do addition. Although we do one shift operation, one addition. Yeah. But we also know addition is slower. So we like to, slower means it takes more execution time. So we like to focus on the slower part, the costly part, addition. Yeah. Here, let us use a function a of n to represent the number of additions when we do the calculation. Okay, yeah. All right. So the recurrence relation will be a of n equals a of floor function of n over 2 plus 1. That's our main recurrence relation, but we need a base case. A of 1 equals 1. Yeah. A of 1, some of you may argue, could be 0 because we do not need to do addition. Yeah, but here, in order to make it close to our original problem, yeah, we make it a 1 because it's not a big deal, right? Just one difference from 0 to 1. The good thing is, if we solve this problem, then the solution is the same as the original problem, right? Because the structure is exactly the same. Okay, yeah. All right, so let's try to solve it. Here, I like to show you the logical thinking procedure or process in solving this recurrence relation. Yeah. First, it's non-trivial. We need to do a lot of work. Second, we can learn many useful things from this example. Okay. All right. How to handle the floor function? In order to solve this recurrence relation, we know the floor function part, we do not feel quite comfortable because it's hard to predict, right? The floor function, sometimes you drop the fractional part, sometimes you do not. So it looks like there is some uncertainty there. If there is some uncertainty, then we need to pay more effort to handle the uncertainty. Yeah. Here, the floor function is 1. Yeah. Let us look at the property for a floor function division by 2 floor function. When n is an even number, its value is m over 2, but when n is an odd function, it is n minus 1, parenthesis, over 2. Okay, yeah, it's simple. We cannot call this expression hard. It's simple, yeah. But there is some uncertainty. In our recurrence relation, if we want to find the exact formula, here, not approximate formula, we want to find exact formula, then that truncation part is not very friendly, all right? Yeah. For our problem solvers, not very friendly, okay? So we want to make it friendly, okay? Because it's not very friendly. Can we make it a little more friendly here? Because we can make friendly assumptions, right? Yeah, it's not friendly, we know, but can we make some friendly assumptions we need, right? Yeah, here we will do that. Yeah, because when we solve a problem, if it is hard, then we can consider simpler cases, right? Yeah. Remember we have an old strategy we used before. Try simpler cases first. Here, we start with simpler cases first. When we start, we do not consider relatively more complicated cases. We want to make our lives easier. So we only consider relatively simpler cases. Here, we do the same thing. Okay? Yeah. How do we make our life easier? So let us, start with this question. What do you wish to have? Yeah, because you have freedom, right? When you start, you have freedom to choose simpler cases. Here, we want to take advantage of that freedom to make our lives easier. All right, yeah. So let's apply that freedom. All right. From the original of this given recurrence relation. Yeah. Because we don't know what is the exact expression of that n/2 floor function. Yeah. So we want to make our lives easier. So we want to look at this. We wish n even. Can we do that? Because when n even, n/2, it's already integer, so we don't need that floor function. The floor function is gone. How about that? So here we make a wish. Yeah. We have that freedom to do that. So we assume n is even. How about that? Yeah. Okay. Yeah. Think about this thinking approach. Thinking approach. Yeah. In this class, I will use this thinking process several times. Here it is the first time. Okay. So we take advantage of the freedom we have, and we make some reasonable assumptions to make our lives easier. So in this step, we wish n even. All right. After that, we need to move to the next step, right? Not done yet. Next step. So we need to this time continue n/2 floor function at the left-hand side because it's n already even. So the left-hand side, the floor function already gone. We don't need that floor function. It's gone. But right-hand side, this n/2, the floor function is still there, right? It cannot be removed. Even if n is an even function, n/4, we cannot say n/4 is another integer, right? You cannot say that. That means the floor function cannot be removed directly. Then let us apply our freedom another time. This time we wish n/2 is an even. number, then the second floor function can be removed, and so on. Okay, think about that. Yeah. Some of you may argue you make too many assumptions. Yeah. Let us assume we can do that. How about that? Yeah, we want to make our lives easier, so let us assume we can do that at this point. All right. So if you can keep doing things like this, keep making the wishes as many as we need, eventually we will have this assumption. Assume that n is power of 2. Then we can do division by 2 all the way to the bottom without any necessary floor function needed, right? Because when we do division by 2, we have integer result. Yeah. Before we reach 1. Yeah. When we reach 1, we're already at the bottom. So we don't worry about that. That's the base case. So that's fine. So we don't worry about the base case. Okay. So look at this. Yeah. We make this big assumption. Assume that n is power of 2. So then all floor functions all gone. Then we simplify the given problem significantly. No uncertainty, right? Yeah. So we have the confidence to solve that problem. So let us solve that version first. Okay. So next step, this time we assume n equals 2 to the kth power, power of 2. Okay. After this assumption, then, although k equals log base 2 of m, because later we need to write k in terms of m. So here, let us put it aside, put this expression k equals log base 2 of m aside. So later we may need to use it. Yeah. After that, our new recurrence relation becomes this one. Yeah, look at that. A of 2 to the k equals a of 2 to the k minus 1, parenthesis, and plus 1. Yeah. The good thing for the new recurrence relation, the floor function is gone. We never need to deal with the unfriendly floor function, right? It's a big improvement. Yeah. Next, let's solve the recurrence relation. So do the, work like this. Yeah. The first equation, yeah. Next one, we do division by 2, right? Division by 2, still good expression. Yeah. Another division by 2, and so on, until we reach the bottom, the base case. Yeah. Because this one is base case. So we can stop. A of 1 equals 1, base case. Okay, all right. Now, with this sequence of equations, we just add them up, and do cancellation as much as we can from both sides. Yeah. This diagonal type cancellation. Yeah. Same term, two different sides, so we can cancel them out. Another cancellation, and so on until the last one. Then let us put the remaining terms. What is a of 2 to the kth power? What is that? To do that, we need to count the number of equations. How many lines do we have? So here's the question. Yeah. Here, it's a place to do the counting. Yeah. Here, I like to show you the simple counting technique. Although it's simple, but I'm afraid some of you may not be able to do that correctly. Although I introduced a method for this situation before, but some of you may not be able to memorize it. So I call it counting by reference. Find appropriate reference, one-to-one correspondence. Remember, I explained that before in our module 1, when we do the counting, count the number of additions we used at that time. Here, we need to do that. Okay, our goal, we need to count the number of lines. But due to this ... we may not be able to keep track of all these lines, right? How do you keep track of all these lines with the, many lines skip it in the middle, right? To keep track, you need to find appropriate reference to help you keep track of it. Here, let me find a reference, okay, simple reference. The first line, top line, can we connect to the exponent number k? We connect to k as a reference, okay? The first line has one-to-one correspondence with the superscript k. The second line corresponds to k minus 1 and so on. How about that? Okay. The last line connects to that superscript 1. How about that? Is that one-to-one correspondence? Yes. Now, when you do the counting, you do not need to count the number of lines directly. Can you count the superscripts from 1, 2, 3, until the last one, k? To keep track of these consecutive integers, it's easy, right? When we do the counting, we count these numbers. How about that? K, that's k lines, right? So we can get our answers easily. 2 parentheses, a of 2 to the kth equals k plus 1. Yeah, because this base case, this number equals 1. And there are k1s. So that's the k part. Okay, k plus 1, that is the answer, exact number. Okay, yeah, accurate. Yeah, no approximation here. Okay, yeah. Now, because this formula, this is the answer, but still not exactly what we need, because it's in terms of k. In terms of k, we want some expression in terms of m, not k. K we treat as an intermediate variable, so not original variable. We want to use the original variable. Okay, so we need to make the last step, conversion step. So that is the result, a of n equals 1 plus the k. Now we can use the expression that we saved before, that is log base 2 of n. So that is the final expression. Yeah. So we found that. All right. But this expression only true for n equals power of 2 to the k. If n not equal to power of 2, this expression may not be correct. Okay? Yeah. Because obviously we know log base 2 it's not necessarily an integer, right? Where n is not power of 2, the log base 2 expression, it's not an integer. And but the left-hand side must be an integer, right? A of n must be an integer. Okay? Yeah. But right-hand side is not an integer. So definitely you cannot use this formula when n is not power of 2. Right? Not power of 2. So it is wrong. Okay? Yeah. But our goal, if you want to solve the problem completely, you have to find the formula where n is an arbitrary positive integer. So there is a gap, right? There is a huge gap. How can we bridge that gap? How can we, fix it, that gap? Okay, yeah. That's the next question. Yeah. Because we want to solve this problem completely. So we need to get the answer from power of 2 case to the general case. That's our next step, the general case. Okay, yeah. All right, yeah. So we need to continue the work, right? Continue the work, right? Yeah. So here, for the work to be continued, can we make a guess? Can we make a guess here? Yeah. Guess the answer. Yeah. Let's do this step. Yeah. Because remember, we have a guess and a verify strategy before. If you can make a good guess, then later we can verify if our guess is correct or not. Yeah. So the next step, we like to apply that guess and verify strategy. Okay. Yeah. All right. So let's make a guess. Yeah. Because although we know this expression is not quite right when we move from n is power of 2 to the general n, it may not be exact like this, but can we make some modification to make it close to the correct answer? Yeah. So that's what we like to do here. All right. Make a guess. Yeah. We know log base 2 of n is not an integer expression in general. How can we convert it to integer expression? Is there a simple way to convert a non-integer expression to integer expression in a simple, easy way? Such way, yeah, we have seen it before. Okay, the guess, use the floor function. How about that? If you put a floor function on log base 2 of n, now it becomes an integer expression, right? For any positive integer n, this is an integer expression. But we don't know if it's correct or not, right? This is our reasonable guess, but we don't know if it is a correct guess or not, okay? And then there is another question, why you do not use the ceiling function. Here, because ceiling function also gives us integer expression, right? Why you do not use 1 plus the ceiling function of log base 2 of n? You use the floor function. We know these two are two different expressions. To answer this question, that's easy. You just try some simple numbers. Try n equals 3. Okay, yeah. We use flow function f of 3 equals 1 plus 1, that's 2. Okay, but if you use the ceiling function, the version, you will get 3, right? 2 or 3. Okay, yeah. But 3, yeah, look at that. If you count the bits, 3, that's 1, 1, right? 1, 1, 2 bits. Okay, yeah. But 3, not 3 bits, 2 bits. So that's why we take, flow function version. We do not take the ceiling function version. Okay, yeah, we just do some simple experiment. Yeah, yeah. You may argue, so A means the non-Borel addition, right? Yeah, but we also know because the recurrence relation is exactly the same as our original recurrence relation. So the meaning the same. Okay, yeah. So that's why we can use this simple example for testing, for checking. Okay, all right. Yeah. Then, so here we know this is the best guess we can make. That's the best guess, right? Yeah. But the unknown part is we do not know if it is correct or not. So the remaining step, we need to verify it. We need to verify it to make sure it is 100% correct. Then we can say we solve this problem completely. Okay, yeah, yeah. But that part, verification part, is pretty hard, so I delay it a little bit. Yeah. Later I will come back to solve it. Yeah. But I like to move to the next problem. Yeah. So we can move a little faster. After I complete next problem, then I come back for this one. All right. Yeah. So otherwise, we will spend too much time on one particular problem.